Okay, good afternoon, ladies and gentlemen. Hello, can you guys hear me?
Yes, we can.
Okay, lovely. I hope each and every one of you is all right. For me, I believe in timekeeping. So when we say 12 hours, at 12 hours sharp, we begin. Those that are going to come late, they are going to find us along the way. Next time, they'll try and keep time. So we are going to start from where we ended from yesterday. I hope you guys had revised what we had done yesterday and it's a bit clearer. I also hope you went through the stuff that's left so that it doesn't really cause you a lot of problems today. So just a bit of a recap on what we did yesterday. We introduced the module of Mécanique du point. We started from a general perspective of physics. Then we delved a bit deeper into mechanics and the purpose of mechanics. We looked at the areas in which mechanics is helpful, and we also looked at its limitations. From there, we did a bit of a rappel mathematique, specifically on vectors. So we defined what a vector was, the types of vectors that we have, and we also looked at la notion de repérage d'espace. We defined that. We defined some notions when it comes to repairs. We also looked at what a base is and its characteristics or properties, some would say. We also looked at the representation of a vector. We looked at the formula for calculating the module or the magnitude, in English, the modulus of a vector. Then we looked at the produit scalaire. We looked at the expression analytic of the produit scalaire. We also looked at this formula here for the produit scalaire. We looked at the properties of the produit scalaire. And finally, we ended with the applications of the produit scalaire, hoping that all this was clear. Today, we shall pick it up from the produit vectoriel. Yesterday, we were looking at the produit scalaire. Today, we are going to look at the produit vectoriel. There's something I forgot to mention yesterday on the produit scalaire, and it is that whenever you are calculating the produit scalaire, the answer or the result is a scalar quantity. It's not a vector, it's a scalar, or it's just a number, just a magnitude. So you just write, if the answer is 5, you just write it as 5, and that's it. If your answer is 2, you're just going to write it as 2 because it's a scalar quantity. That's why we call it produit scalaire, because the answer we are getting is a scalar. However, when we are looking at the produit vectoriel, the result we get from this operation of the produit vectoriel is a vector. And as I said yesterday, your answer should be represented with a flash, an arrow on top of it to show that it is a vector. If you calculate the produit vectoriel, you find the correct answer and you leave out the flash, your answer is going to be wrong because it's no longer a vector and you did not do the produit vectoriel. So let's take care. When we are doing the produit vectoriel, the answer is a vector. So we have to represent it with an arrow. So they're telling us here in the first statement that le produit vectoriel de deux vecteurs U et V est un vecteur noté W with a flash on top, where W égale U vectoriel V. So this V we're seeing here, that's upside down. That's how you represent the produit vectoriel. For the produit scalaire, we had a dot, a full stop. For the produit vectoriel, we have an inverted V, like it's upside down. So that's U vectoriel V. That's how you read it. W égale U vectoriel V. Now, one thing you should know about the produit vectoriel is that when you calculate the produit vectoriel of two vectors, the resulting vector is perpendicular to both vectors. So if you've been given two vectors, U et V, you're calculating leur produit vectoriel. Le résultat qui est W dans ce cas sera perpendiculaire à U et V. it's going to be perpendicular to both U and V. At the same time, the answer, as they are saying here, la direction est perpendiculaire au plan formé par U et V. So you get two vectors U et V. When you connect them to the origin, they form a plane. And then when you calculate the product vectorial, you are getting a resulting vector that's perpendicular to both of them. As in the example of the figure below here, we have U and we have V and an angle alpha between them. The resulting vector W is perpendicular to both of them. So if U and V belong to the horizontal plane or the horizontal axis here, they are in the horizontal plane. V is going to be in the vertical plane for it to be perpendicular to both of them. What's important to remember here is that W, the resulting vector from the product vectorial here, is going to be perpendicular to both vectors at the same time. Is that clear so far?
Yes.
Okay.
Sorry, can you repeat explanation?
Okay, repeat the explanation. Starting from where?
How it's perpendicular and stuff.
Okay, so we were saying today we're going to begin with we're going to do the product vectorial. Yesterday we did the product scalaire. Now the product vectorial. So they're saying we have an example here. They're saying le produit vectoriel de deux vecteurs U et V est un vecteur noté W. We just take it as an example. We have W as a product vectorial of U and V. So the rule of the product vectorial is that the resultant after you do the product vectorial of two vectors is perpendicular to vectors you are calculating the product vectorial for. So in this case, we are calculating the product vectorial of U and V, the answer being W. That means this answer here, W, is perpendicular to both U and V. That's just how it is. If they tell us to find the product vectorial of two vectors A and B, we're calculating A vectorial B. The resulting vector we are going to get from that operation is going to be perpendicular to both A and B. So it's represented here geometrically in this figure or graphically. We have two vectors U and V. We are calculating their product vectorial. The answer W is perpendicular to both of them. As you can see here, it's perpendicular to this and it's also perpendicular to that. So if U and V belong to the horizontal plane, as they are here, the horizontal plane there on the ground, we can say W is going to be going up. It's going to be in the vertical plane so that it is perpendicular to both of them. But that's just the general rule. When you're calculating the product vectorial of two vectors, the resulting vector is perpendicular to both of them. Is that clear?
Oui.
Okay, lovely. On avance. Then on the direct part, I told you I was going to explain to you guys later on, so we can just skip it for now. We won't need it up to this point. I'll explain to you when we need it. So we come to the third point. So norm. The norm is the magnitude, the modulus, le module. It's the same thing. So sa norme est donnée par. Remember this formula, we saw it yesterday, except for in the product scalaire, it didn't have these lines indicating the magnitude. The product scalaire was just the answer like that, but in the product vectorial, it's the norm. So we have W being equal to the module of W being equal to module of U multiplied by the module of V multiplied by sinus. In the formula for the product scalaire, we had cosinus. In the product vectorial this time, we have sine of the angle between the two vectors U and V. That's what's changed in this formula. So it's just like the formula we had yesterday, except in this case, we're calculating the modulus of the resulting vector, and we have sinus instead of cosinus here in the formula. So if you learned how to use the other formula yesterday, this formula is not going to give you problems. Does it mean that they form three dimension? Yes, yes. It means the three of them put together become three-dimensional. Then, sorry, I had network problems, so I've understood anything from the product vectorial. Is your connection better now, Paul? Can I re-explain? You can hear me now? Paul, can you hear me now? Okay, yes, lovely. So I was saying the product vectorial, number one, product vectorial, it is noted or denoted with this V that looks upside down, the upside down V, we can call it. So whenever you see this operation, just know they're asking you to calculate the product vectorial. So in this case, we read it as W equal U vectorial V. W is equal to U vectorial V. Then the general rule is that when calculating the product vectorial, the resulting vector from that operation is perpendicular to both the two vectors whose product vectorial you are calculating. So in this case, we have W equal U vectorial V. W in this case is perpendicular to both U and V. That's just how it is. When you calculate the product vectorial, the resulting vector is perpendicular to the two vectors whose product vectorial you are calculating. And it is represented here in this figure. They're trying to show us that if we're calculating the product vectorial of U and V, the resulting vector W is in this sense here, this direction, where it is perpendicular to both U and V. Is it clear? It's clear? Nice.
Oui.
So we come to the norm here, as I was explaining this formula. I even highlighted it. You just have to know it. And then the product vectorial, what does it represent? Why calculate the product vectorial? So it is explained here. The product vectorial represents the surface formed by the two vectors, or of the plane formed by the two vectors. So if we have two vectors here, U and V, we're calculating the product vectorial. The product vectorial, the answer we'll be getting is the area of the plane formed by U and V, or the parallel formed by these two. So there and V there, when you just project this and project that there, the plane they'll form, this plane here, or this parallelogram they're forming here, the area of it is the product vectorial. Is that clear?
Yes.
Oui.
Okay, good, good. So we now advance to the properties of the product vectorial. Number one, the product vectorial. Oh, yes, yes, sir.
Yeah. W is perpendicular to both V and U, but
Yes.
on the perpendicular part, how is W perpendicular to U? As you can see on the diagram, they don't look perpendicular.
No, the diagram is not drawn to scale. Don't expect a perfect diagram. Just imagine they are perpendicular here. Obviously, the person that was drawing did not really take care to make sure it's perpendicular, but it's supposed to be perpendicular. So in your mind, just try to imagine something perpendicular. You get it?
Yeah, I get it.
Yeah, it was just poor drawing, but normally they're supposed to be perpendicular. Okay, so we advance to the properties. Number one, if you remember yesterday, we said the product scalar is commutative. The product vectorial is not, unlike the product scalar. the product vectorial is anti-commutative. It's not commutative. So when you calculate E vectorial V, it's not equal to V vectorial U. They are not equal. Actually, it's the opposite. I think the other one is negative of the other. Then le produit vectoriel est distributif par rapport à l'addition. I explained what this yesterday. I don't know if you guys revise that and remember, but it is like this. So if you have E vectoriel entre parenthèses V plus W, it's going to be equal to, if you expand this expression, the answer is going to be the same, where you have E vectoriel V plus E vectoriel W, because the product vectoriel is distributive rapport addition. Then finally, when U is not equal to 0, V is also not equal to 0, if the product vectoriel is equal to 0 of these two vectors, U and V, it means U and V are collinear, or they are parallel. I'd like someone to try and explain this for me. That's using trigonometry again, from this formula here. And someone tried to explain to me why, if we have U different from 0, E different from 0, but the product vectoriel is equal to 0. Okay, let me say repeat the first property. Before I repeat the first property, can someone try to tell me why this is so? Just a wild guess, or maybe you know the answer. Someone to try.
Because when lines
Why,
are
if they are
parallel,
Uh-huh.
means they're either at 360 degrees angle or 0 degrees and sine 0 or sine 360 0.
Exactly, perfect. That's correct. If they are collinear, it means they are either at 0 degrees from each other, or you can also say 180 degrees. Now, 180 degrees, they're in opposite directions. One is going this other side, the other one is going in the opposite direction. For all of them, both at 0 and at 180, and even at 360, the sinus is equal to 0. That's why if the product vectoriel is equal to 0, and both vectors are parallel vectors have a product vectoriel equal to 0. The first property, language, the vectoriel est anti-commutative. It means U vectoriel V, the product scalaire, where we have A scalaire B égale B scalaire A. If you interchange them or you swap them, the answer remains the same. For the product vectoriel, it's different. The order matters. If you swap their order, you get a different result. It's clear?
Oui.
Okay. Expression for calculating the product vectoriel. We have this one that gives us the norm or the modulus of the answer, but in most cases we are not interested in the modulus. We want the representation of algebra. I believe you guys have never seen up until this point, because in high school we did matrices, but I think we're just mostly dealing with 2 by 2 matrices. When we calculated the determinant, it was for 2 by 2 matrices, not so. Have you guys done 3 by 3 matrices before? Did you do 3 by 3 matrices in high school? For calculating
ADMA, yeah.
determinant. In ADMA?
Yeah.
Yes.
Okay. Then some of you have seen this before. So in calculating the product vectorial, we form a matrix we have, and then we calculate the determinant of that matrix. Okay, we form a matrix, then we calculate the determinant That's the product vectorial. The woman made a mistake when she was writing here because you're saying x3, y3. Normally, we're not supposed to have this. So I put an x here to indicate that this is wrong. We're not going to work with this expression here, x2, y3, x3, y2. It's wrong. Just ignore it. Come down here to these numbers between lines. So when you're calculating the determinant of a matrix, first of all, you use hard lines like this, hard straight lines, to show that you're calculating the determinant. So here the base vectors, we have E, G, K. We write them in one row like that, E, G, K. Then you get the first vector in your expression. As I said, the order matters here. If you swap the order, the answer is going to change. So here we have E vectorial V. To get the first vector, which is U, we'll write it x1, y1, z1, the coefficients, these ones, the coordinates, we'll write them there. Then we get the second vector again, we'll write them in the third and last row. We'll write x2, y2, z2. If I write the base vector E here, that means in this column, I'm only supposed to have the vectors that are following the E. That means the x coordinates in this case are the ones that are following the E. We write them there. We have G here. We are just going to write in this column the vectors following G, and that's why, or sorry, the coordinates following G. That's y1 and y2. Same thing for K. So when we form this matrix now like this matrix here, we are to calculate its determinant, and the determinant is what's going to give us the expression vectorial of the product vectorial we are. What you do is, normally you can calculate it by just looking at it, but for beginners, for those that are seeing it for the first time, what you do is you come on the eye here. If you're using a pen, paper, and your hands, you can hide. Yeah, like for me, when I was learning, the person that was teaching me, and also most beginners, what they do is you put your finger on the eye. When you put your finger on the eye, you cancel out the row in which the eye is, this row here containing G and K, and also the column in which the eye is, you cancel them out. After putting your finger on the eye, you cancel out the column in which the eye is and the row in which it is. Then you extract the remaining matrix. So when I put my finger on the eye or the pointer on the eye, I cancel out this column in which the eye is, the column containing in x1 and x2, and I cancel z1 and z2. So I extract this matrix here, this 2 by 2 matrix, and I write it down here. And this matrix will be following I. I forgot to put a flash on the I. So this will be the calculation that's going to give us the coordinate for the I in this case. How to come up with matrix. So when coming with the matrix, number one, what you do is you get the base vectors. The first row of the matrix is going to contain the base vectors, E, G, K. In the first row, you get the base vectors. When you write the base vectors, the second row is going to contain the coordinates of the first vector. As I said when I was explaining the first property of the product vectorial, I said the order matters. The order, you change the answer. And this is why. Because when forming the matrix, you have to get the first vector first. You get its coordinate vector. So we get its coordinates, x1, y1, and z1. We write them in this row that follows. Then finally, we get the second vector. Its coordinates, we write them in the last row like that. And when writing this matrix, we do not use brackets like in normal matrices. We use straight hard lines because we are calculating the determinant in this case. It's a determinant we are calculating, so we use hard lines like that. Is it clear, CK?
Yes, it's clear.
Okay, lovely. So now we are extracting the vectors. So as you learn sorry, I didn't mention this before. When calculating the determinant, see, when you do it in algebra, it is that calculating the determinant for a 2 by 2 matrix is easy. It's easy because it's just major diagonal minus minor diagonal. I'm sure we all remember this when calculating the determinant for a 2 by 2 matrix. It's just major diagonal minus minor diagonal. But when you advance from a 2 by 2 matrix, you go to 3 by 3, 4 by 4, 5 by 5. There it becomes complicated because you can't do major diagonal minus minor diagonal. You have a lot of rows and columns there. So what you do for these matrices is you reduce them to you start reducing them. If you have a 5 by 5 matrix, you'll be reducing it from 5 by 5 to 4 by 4. You break it down. From 4 by 4, again, you break it down to a 3 by 3. From a 3 by 3, again, you break it down to a 2 by 2 until you reach a 2 by 2. That's easy to calculate. So here we have a 3 by 3 matrix. What we are aiming to do now is to try and decompose it into 2 by 2 matrices so that we can calculate their determinants. That's how you normally calculate the determinant of greater than or of order greater than 2 by 2. So we have a 3 by 3 matrix here. Our aim is to break it down or to decompose it into a 2 by 2 matrix. So what normally in algebra is you are going to pick one row or one column that you will be covering with your finger, as I mentioned. So if I pick the first row, for example, this one containing E, G, K, I'll come to the I, I'll cover the I with my finger, and I'll eliminate the row and the column in which the I belongs. And I'll get the 2 by 2 matrix that's left, and I'll multiply it by I to show that it was the I that helped me decompose it this way. We are still in the first row that we chose, so we move to the J. You are going to put your finger on the J again, and you cancel or eliminate the column and the row in which the J belongs. So in this case, the J belongs to the second column. So you cancel out the second column and the first row. You remain with X1, X2, Z1, and Z2, and you extract it as your second 2 by 2 matrix there. You come to the K again. You put your finger on the K and you eliminate the row and the column in which the K belongs. So we'll remove the first row and we'll remove the last column, and we'll be left with X1, Y1, X2, and Y2, and we'll extract this 2 by 2 matrix there and multiply it by K to show that it was the K that helped us eliminate it, learn those sophisticated matrices. In algebra, that should be at the FST in GGM, we learn it in algebra too. I don't know about the rest of the schools, but when you start doing matrices, it should be in algebra too, and you do algebra too. But it's a bit further in algebra. Then the minus, okay, someone asked about the minus. I was just getting there. So normally there's a rule. The rule is that you go plus, minus, plus, minus, plus, minus, plus, minus, just like that, down the row or down the column. So the I is going to be plus, the J is going to be minus, the K is going to be plus. If there was anything after the K, it was going to be minus. After that, we'll have a plus, just like that. If we're going down this column, we would have had plus, minus, and plus, minus, plus, minus, just like that. That's why we have the first expression here being positive, then the second expression being plus. It's just like that. It goes in that order: plus, minus, plus, minus, plus, minus. When calculating the determinant, it's just like that. Is it clear up to this point?
C'est clear.
Okay, I said it's clear. We'll look at an example, a numerical example to help us understand more. I put an example here. So I said, soit deux vecteurs U et V, U égale 5I plus 2J plus 3K, et V égale I moins 4J plus K. Then we say W égale U vectoriel V. And they're asking us to calculate W here. You see, calculate W. So now we first have to form the matrix. So the first thing we're going to do is we're going to get the base vectors. As I said before, we'll write them in one row. The first row there, the base vectors, we'll write E, G, K, because in our vectors we had E, G, K as our base vectors. So we write them like that. Then our question is E vectorial V. So we'll get the first vector in this expression, which is E, and we'll write its coordinates in the second row. So we have 5i, 2j plus 3k. So suivant i, we write 5. Suivant j, we write 2. Suivant k, we write 3, like that. Then we get our final and last vector, which is v. We get its coordinates. We just have e here. It means there's a 1 in front of it. So we get 1. Then we have minus 4j. That means we have moins 4. Finally, we have k, no coefficient, that means there's a 1, and we have a 1 there. So our matrix is like that. And for us to calculate W, le produit vectoriel, we use hard straight lines to show that we are calculating the determinant of this matrix. So now we get into the calculations. So as I said, we begin with the coordinate for I. We are going to cover the I, and I will eliminate the row and the column in which the I belongs. So I will eliminate the first row here with G and K, and I will eliminate the first column because the I belongs in the first row and the first column. I will remove them. What I'm left with is 2, 3, minus 4, and 1. So I write them here. Suivant E. This is what's going to give me the coordinate for E. Then I move to the G. And as I told you, we go plus, minus, plus, minus. So the first one was a plus. The second one for the G is going to be minus. And what we're going to do is we're going to cover the G again. If you're doing it with a pen and paper where you are, you can just put a finger. It's easy to eliminate them that way before you get used to it. So when I cover the G, I will eliminate the second row in which the G is this row. I'll remove it. And the first, sorry, this is a column rather. The second column, I'm going to eliminate it. And the first row, I will also eliminate it. What I'm left with is 5, 1, 3, and 1. So I will get them as my second 2 by 2 matrix suivant G. Then afterwards, as I said, it's plus, minus, plus. So the car is also going to be plus. We write plus, and then we cover the car. What we're going to do again is eliminate the row in which the car belongs, which is the first row, and the column in which it belongs, which is the last column here. So we eliminate this and we eliminate that. We'll have 5, 2, 1, and minus 4 as our 2 by 2 vector there, suivant car. So now we have decomposed it into 2 by 2 vectors. Now from here, it's easy to calculate the determinant of these 2 by 2 matrices because it's just major diagonal minus minor diagonal. So the determinant of this matrix here is going to be the major diagonal, which is 2 and 1. So it's going to be 2 times 1 minus the minor diagonal, which is minus 4 and 3. So we'll have 2 times 1 is 2 minus 3 times minus 4, that's minus 12. So we'll have minus minus plus, it's 2 plus 12, that's 14. So we have 14i as the coordinate for the I there. We have 14, we write it. We come to the next matrix here, the 2 by 2 matrix here. Still same rule, major diagonal minus minor diagonal. So it's going to be 5 times 1 minus 3 times 1. It's going to give us a simple 2, and we have a minus there, so it's going to be minus 2j. And finally, we come to the last matrix there, 2 by 2. Still the same rule, major diagonal minus minor diagonal. 5 times 4 is minus 20, minus 2 times 1, which is 2. So we have minus 20 minus 2, that's minus 22k, and I minus 2j minus 22k. Of course, not forgetting the arrows, the flash, do not forget them when you are writing vectors. Produit vectoriel, the answer is a vector, so it should have a flash first of all. When you write the W, you put the flash on top of it to show it's a vector, and also on the base vectors, there are vectors, so you also write arrows on top of them. Is that clear?
Oui, c'est clair.
Yes.
Oui.
Okay, great. That's lovely. We'll do this. You guys, I'm going to give you 5 minutes. 5 minutes, try to do this exercise 1 here. In 5 minutes, try to do it and just post your answer in the chat box. In 5 minutes, the time is 12:36. At 12:41, we shall continue our lesson. So try it wherever you are, just for the sake of practicing. 5 minutes time, quick. Yes, David Mulena, only exercise 1, just the first question. Ça, c'est très bien. Ah, John Banda, you can check. You can try to redo your work. But for everyone else, c'est très bien. C'est très, très bien. Minus 3i plus 6j minus 3k. Oui. C'est correct. Lovely, guys, lovely. Yeah, when sending your messages, just try to change the settings to send to everyone so that people can be seeing your questions also and your answers too, in case someone is stuck. Yeah, don't send them to me privately, just send to everyone. But I see you guys have gotten the concept. It's correct, your answers are correct, so we can advance. Revise these questions we have here. Maybe I'll just give them to you as an assignment for the weekend, since you guys have understood the stuff. Love this. Okay, what's going to follow now is nothing complicated. The formulas might look complicated, but c'est juste des choses simples. So what we're going to begin with now is the double produit vectoriel. You guys are with me, huh? Everyone is with me? I can advance?
Yes.
Yeah.
Okay. Great. Le double produit vectoriel. So as the name seems to imply, double produit vectoriel, you are just doing the product vectorial. I give you to add three numbers, 1 plus 2 plus 3. So it's a double addition because you're doing the addition twice. Same thing for the product vectorial, just doing the product vectorial twice, sorry. And you have formulas like this in Mécanique du point with two product vectorials. And there's a formula here. Here there's just one in mind. You can just master it. When you have double produit vectorial, it's either you can first calculate the product vectorial of V and W, then you calculate the product vectorial of U and the answer you get from there, or you can use this formula here where you say U vectoriel V vectoriel W égale entre parenthèses, between parentheses, U scalaire W scalaire V moins U scalaire V scalaire W. Just this formula. You can try it if you want. Just come up with 3 vectors, then try to calculate the product vector, double product vectorial directly like that. Then try to use this formula on my right hand side, this side. See if you get the same answer. You are supposed to get the same answer. If you don't get the same answer, then you know you're making a mistake somewhere in your calculations. It's an opportunity for you to practice. But that's the formula. That's how it is. You can find a way of memorizing it if you want. That's a memory aid to help you remember. Or if you're not good at remembering stuff, you can just go the long way. Just calculate the product vectorial twice. You won't lose anything but time. Then we come to the product mixed. Product mixed, again, as the name implies, you are now doing both the product vectoriel and the produit scalaire. C'est le produit mixte. Le produit mixte des trois vecteurs U, V et W est un scalaire. Who can tell me why it's a scalar? Just from this expression here, that where my pointer is. Can someone tell me why the final answer is a scalar quantity? Going once, going twice. No one. Someone to try.
Is it because it presents the volume?
Direction.
Side.
Huh? There's no direction. Okay.
I think I can give it a try.
Yeah, there's no direction. Yeah, try.
The vector produit, when you multiply it, it will give you a number. right?
No, the product
The
vectorial is
produit
supposed
is
to give you
scalar.
a vector. Yeah,
Yeah,
product
to give
scalar
you
is
a
supposed to
vector.
give you a number, scale. Yeah. Can Okay. Yeah, okay, I'll tell you guys it is so. When you look at board math, let's say we'll begin from there. The first operation we'll be performing here is the one in the brackets, not so. That's a rule of mathematics. You always begin with what's in the parentheses. So the first operation we'll be doing will be the product vectorial, okay? And the product vectorial, as then before, the answer is going to give us is going to be a vector. That's why they call it product vectorial. The resulting answer is going to be a vector. So after we do the product vectorial and we get our vector from these two, we are going to now calculate the product scalar. It gives us a scalar. That's why they call it product scalar. The final answer is a scalar. That's why the product mixed gives us a scalar quantity, because the final or the last operation we're doing is the product scalar, and the final answer from the product scalar is supposed to be a scalar quantity. Was that clear?
Yes.
Can you just
Yes.
kindly repeat the same statement, sir?
Okay, I said the reason why the product mixed gives us a scalar as an answer is because from mathematics, we know that the first operation we do in an expression is the operation between brackets, on parentheses, between parentheses. That's where we begin. So in this expression of ours here, we are going to first calculate what's in the brackets, which is the product vectorial. And we know from the definition of the product vectorial that the resulting or the resulting answer or the result is a vector. That's why we call it product vectorial. The answer from the operation is a vector. So when we first perform this operation, the answer we'll get will be a vector. Then finally, we are going to calculate the product scalar of each answer we get. And we know again from the definition of the product scalar that the answer or the result from the product scalar is a scalar. That's why we call it product scalar. The result is a scalar. So the reason why the product mixed in general is going to give us a scalar as an answer is because the final operation we are performing in this expression is the product scalar. And if the final operation we are performing is the product scalar, it means the answer is going to be a scalar. It's clear?
Yes, it's clear.
Okay, lovely. Then they're telling us here that the product mixed, what does it represent? So the product mixed, you have three vectors. You have three vectors. In this case, we have E, V, and W. So we saw from the product vectorial that the product vectorial is going to give us the area of the plane formed by the two vectors. You guys remember that, not so? From here, we said here, where? Here. We said the product vectorial is going to give us the area of this plane formed there, okay? So when we come down here in the product mixed, we have V is a parallelogram, this one down here, or this plane. And this operation V vectorial W will give us the area of this down here. Now, what's the product mixed going to give us? The product mixed, we introduce this vector that there, and we notice that these three vectors, they form we call a parallelepiped. It's hard to read. Parallelepiped. this word here. I'm sure there's people who are better at pronouncing stuff than I am. It's a parallelepiped. So these three vectors put together with all the projections and all, they form a parallelepiped. It's like a cube, but it's slanted. The way a parallelogram is a slanted square, this one is like a slanted cube or cuboid. Okay, I was saying the reason why the product mixed gives us a scalar is because the final operation we are performing in this operation of the product mixed is the product scalar, because from mathematics we learn that we are supposed to begin with what's in the brackets. So we'll begin with the product vectorial, and the product vectorial will give us a vector as a resulting answer. And then we will calculate the product scalar of E, and that result we got from the product vectorial. And that's going to give us a scalar quantity, because the product scalar results in a scalar. The answer from a product scalar always, toujours, is going to be a scalar quantity. And so the reason why the product mixed gives us a scalar is because the final operation we are performing in this expression is the product scalar. And if the final operation is the product scalar, it means the final a scalar. Is it clear? Who was that asked? I've forgotten the name. Semicolon. Semicolon, it's clear? Okay. So the previous form gives us the volume of this shape these guys form. Okay. The product mixed that we have here is going to give us the volume of this shape. And there's a proof here.
I have a question.
Yes, please.
The product vector, in other words, is giving us the area. And
Yes.
are we free to say that that area itself has magnitude?
Yes, the area has a magnitude. It's the size of the area. When you calculate the area and you find the area is size.
Okay.
Yeah. So if you guys can tell me, what's the general expression for the volume? Volume is equal to what?
Length
Oh, sorry, I
multiplied
meant
by the radius and the height.
Brother Charles, I meant direction. Does area have direction?
No, the area is it's a scalar quantity. It doesn't have direction.
But here we are finding it under the product vector, which is like
the product vector. So when you get the magnitude of that area, it's going to give you the area itself. You might get a vector, but what's going to give you the surface there is going to be the magnitude of that vector.
Okay, okay.
You get it, huh?
Yes, I do.
Okay. Because even here, you see this surface here, it's been represented with a flesh on top. But if you have area in the form, it doesn't have meaning, because area will need the space for us to know the area. And that's why we are just going to get the. So I asked what the volume is. Someone said it was the length, the breadth times the height. Not so. And in other terms, we can say it's like base area or the surface area multiplied by the height. n'est-ce pas?
See.
Yeah, so it's base area multiplied by the height. And the base area is this parallelogram here formed by W and V. And we know that we can find the area of this shape by calculating the product vectorial of V and W. You guys remember the application of the product vectorial? It gives us the surface area of the parallelogram formed by the two vectors. So it means we have the surface area of this shape here in this expression of the product vectorial. So what's left now is working out the height and finding the volume of this parallelogram. Okay, so we are going to denote the V vectorial W with S, representing the surface, because we know S represents this shaded region here, the surface. So V vectorial W is going to give us S. Then finally, we are going to perform the last operation, which is the product scalar of U scalar S, as you can see from here. After we calculate S from here, we bring it down here, we say U scalar S to finish off the product mixed. So U scalar S, from the expression we got yesterday, we know that this is equal to magnitude of S multiplied by the magnitude of U multiplied by cosinus of the angle formed by the two vectors we have here, which is U and which is S. Something worth remembering, or the resulting vector from the product vectorial is perpendicular to both vectors. So if I have V and I have W here, and I calculated the product vectorial S, the direction of S is such that it is perpendicular to both these two. So S is going to be in this orientation there. This is going to be the vector representing S, perpendicular to both V and W. This one here, this S here, that's what they are writing there. And then we are calculating U scalar S. So it's like we're calculating the product scalar of these two angles here, as I'm showing by my pointer. It's U and S with this angle between them here, angle between them there, U, S. And then we said for the product scalar, we can project, like if we're calculating the product scalar, we project from the extremity of U 90 degrees to S. From U, we project 90 degrees to S, and we'll get the product scalar. This H here down here is the product scalar U, S. U, S gives us this H there, if you guys remember from what we did yesterday. There's something I want to try. I don't know if it's going to work. I've joined the meeting using my name. So you guys can just try and click on Charles. Charles, I think I'm using the name Charles. Am I? Yeah, it's under Charles Nkalandula. So I want to show you something I wrote in a paper. Unfortunately, I didn't manage to take a picture of it and be able to share it on the screen. So I'll just try and use my video. Okay, so what you should do is try clicking on my name there, Charles Nkalandula. Or click on the options button and pin the video. Yeah, click on the options button and pin the video. Have you guys managed to do so?
Yes.
Yeah, so you can see what I'm taking a video of here.
Is a triangle is cos theta is equal to h over u cos alpha.
Okay, so you can see it. We are going to advance. So I extracted this triangle from the projection we made, because remember we had a
Excuse me, I
parallelogram.
can.
You can't see.
No, I'm not sure of how to do it.
Go on the participants. You go on the participants. The person that was asking, are you with me?
Yeah, Blonder.
Okay. Go to Charles Nkalandula. Where is Charles Nkalandula?
Okay.
Yeah. Then when you just hover over the square there, or I don't know, it's going to give you my dots, like my dots are going to appear. An options button. So when you click on the options there, it's going to give you options. Just click on pin video.
All right.
You can see it now?
Yeah.
Okay, lovely. So I hope everyone has managed to do so. So we had the parallelogram. The parallelogram we had, maybe I can try to draw it this side so that people are not so lost. I'll draw it on the side here so that you remember what we were looking at. Okay, I haven't drawn it so nicely, but it was looking something like this. Now, my area of interest is just this part here, the part I've shaded here. That's the triangle I've extracted on this side, because I had S, then I had H on the figure there. I had H going up to there. Then we have this vector being U, the vector this side. So we have U, we have H, and we have the vector S. Then we have the angle between them, which I've called alpha. And then what we did was we projected from U down to S, meeting S at 90 degrees. So this triangle is a right angled triangle. So I've extracted this triangle and I've drawn it properly here now. I have this line coming from U. We have U as the hypotenuse, first of all. Then we have this line we projected from U down to S, meeting S. This line down here is S, meeting S at a right angle or 90 degrees. Then we have the angle between U and S, being alpha and there. So now, from SOHCAHTOA in trigonometry, I'm sure you guys all know this. We know that cos of this angle alpha there is going to give us the adjacent side to the angle, which is H, going from there to there in the triangle, over the hypotenuse, which is U. So cos of alpha is going to give us H over U. That implies that this H, this length of H here in the triangle is going to be U multiplied by cosinus of alpha. That H is going to be U times cosinus of alpha. Now, in our calculation for the product mixed, we ended here where we're calculating U scalar S. And U scalar S gave us the module of S multiplied by the module of U multiplied by cosinus of alpha, alpha being the angle between U and S. Okay, and we know from this expression that we derived there, this expression here, that H is equal to U cosinus of alpha. H is equal to U cosinus of alpha. And here we have S u cos alpha. So this u cos alpha here, we can replace it with h being the height, because from the parallelogram, h was this thing here. It was the height of the parallelogram, okay? So we have u cos alpha being equal to h, which finally gives us s times h. S is the surface of this parallelogram here. We said h is the surface formed down there. And I remember we all agreed at the beginning of these calculations that the volume is equal to surface area times the height being h here. We all said volume is equal to surface area times the height. And when getting the height, the rule is that the height should meet the surface at 90 degrees. This is mathematics. It's nothing out of the ordinary or nothing new. It's just mathematics. When you're getting the height, when calculating the volume, you use the height meeting the surface area at 90 degrees. So we had to derive this h, because h is the one meeting the surface area at 90 degrees. And that's why the product mixed is going to give us the volume of this parallelepiped. I don't know if that was clear. Maybe I was a bit too fast.
Repeat.
Kindly repeat.
Okay. What they're telling us is that the product mixed is going to give us the volume of this parallelepiped, this entire parallelepiped, its volume. The product mixed is going to give us that. So we have our product mixed, in this case being U scalar V vectorial W, like that. This is our product mixed, So this expression should give us the volume of this. And what we're trying to do now here is to show or to prove that indeed this expression is going to give us the volume of this figure there. We have our V there and we have our W there. And then from mathematics, we know that the volume is equal to area times height. You all agree, not so?
Yes.
Yes. Volume is equal to area times height. And that's what we are going to work with, because we're trying to show that the product mixed is going to give us the volume. So the volume is equal to area times height. Okay, thank you. Area times height. So area in this case is not just any area, but the base area of the figure you have. And in this case, our base area is this area down here that I shaded, this area down here. This area down here, the area down here, that's the base area, okay? The base area. And then the height, you could have used U, this height here, but U cannot be used as a height because U is not meeting the surface area at 90 degrees. Whenever you are getting the height of a figure, you use the one meeting the height meeting the figure at 90 degrees. It's just the rule. Even you as a human being, when you go to a machine that measures your height, when you're slanted a bit, maybe you're forming an angle of 70 degrees to the ground, you won't get an accurate height. If you want an accurate height, you have to be perpendicular to the ground. That's when you get your true height. So even us here, when we are getting the height of this figure here, we have to get the line or the height that's meeting the figure at 90 degrees, which in this case is going to be this h this side. It's meeting it at 90 degrees because we projected from U here, we projected this line going to meet S at 90 degrees. So if this line is meeting S at 90 degrees, that means, it's not from this, it's because S is the resulting vector from the product vectorial of V and W, and we know that the resulting vector is perpendicular to the two vectors. So we have V and W there. The resulting vector S here is going to be perpendicular to these two. And then this height here is just because it's the same height as U, even though U is slanted, but H is the same height as it. So we'll use this H here as the height because it's at 90 degrees to the surface. So now we had calculated the product vectorial of V and W, and this is obvious. V vectorial W is going to give us the surface there from the definition of the product vectorial, okay? And we are going to call V we're going to call this S. So we say S is equal to V vectorial W. Here, S is equal to V vectorial W. So now from this expression here is going to become U scalar S. From here, we say U scalar V vectoriel W or S égale V vectoriel W. So that means we just replace the S there and we have U scalar S as that there, our expression there. Now, we still want to show the volume. We still want to show the volume. So what we are going to do is we are going to pick it up from U scalar S that we found this side, U scalar S. Now from the definition of the produit scalar, we said the produit scalar U scalar S is going to be equal to the module of S multiplied by the module of U multiplied by cosinus of alpha. N'est-ce pas? That's the definition of the produit scalar. It's module of S times module of U times cosinus of alpha. Then what I did now is to help you guys understand properly, I extracted this triangle here. This triangle, I extracted it. If you want to do your calculations properly, you should gain the habit of extracting things because you'll get confused when you're doing all your calculations on the same figure. So it's better you extract a figure, you draw it separately, you do your calculations there, you get your answer, then you go back to the main figure. So I extracted this triangle there and I drew it here. So I have my S. This is the S going inside, which in this figure here is this S. Then I have my U there, which is this U there. Then I have this line going from U to S, which is this line going from U to S. Then I have my angle between U and S, alpha, which is this angle, alpha, between U and S. So we say this. From trigonometry, here, cosinus of alpha is equal to adjacent over the hypotenuse. Cos of alpha is the adjacent over the hypotenuse. The adjacent to this alpha here, in this case, is this H. This H. H is just a line on S because S is long, but we just want something going up to the height of the parallelogram because we want the height in this case. So we'll get this H going from the origin there up to the height of the parallelogram. Instead of using S, we'll use H. Okay, so we'll just say H over U, H adjacent U hypotenuse. And then what we're going to do here now is we're going to make H the height subject of the formula. We'll have H being equal to, just from here, if you make H subject to the formula, you just take this U to the other side there, you have H being equal to U cosinus alpha. So we have our expression here. H is equal to U cosinus alpha. H, U cosinus alpha. We write it like that. Then we come down here. We are still calculating this expression here, U scalar S. So U scalar S, we said is equal to module of S multiplied by the module of U multiplied by cosinus of alpha. But we have shown that U cosinus of alpha is equal to H from here. H is equal to U cosinus alpha. So we are going to replace this U cosinus alpha simply by this H here. And our expression is going to be S times H, because this expression here, U cos alpha is equal to H. So we just have S times H, which is equal to S times H. Now you notice something. S, we said, is the surface area, the base area. And then H, we said, is the height because it's meeting the surface area at 90 degrees. So we have the volume, which is S times the height. The surface area times the height is equal to volume, proving that the product mixed here, this product mixed is going to give us the volume of this figure here, the parallelepiped. Yeah. Was that not clear too? Chapter, or is it clear?
It's clear.
The one that is given, is it the S or the H?
Sorry?
The one that is given, is it the S or the H?
Neither of them are given. Both of them have to be
No, okay,
found.
calculated first. Which one
Calculated
is it?
S, we calculated S because S
Yeah.
is the surface area formed by the two vectors V and W. S is simply calculated from the product vectorial of V and W, which is what's in the brackets of the product mixed.
Yeah, it's still hard. Then how did you get to the H?
How I got the H was that we just came to this vector representing the surface, because when you calculate V vectorial W, it's going to give us a vector perpendicular to both of them, okay? The vector perpendicular to both of them is going to be this one, the S. But the S is not the exact height of the parallelepiped or of the figure. It can be something longer than that or something shorter than that. So we just got H, a part of S, which is the exact height of the parallelepiped. You see, H is just going from there to there. H is just ending right where the parallelepiped is ending, so that it gives us the height.
Yes, but obtaining the value of H.
Obtaining the value of H, we are going to use U cos alpha.
Okay, okay.
From the right angle triangle, there. So it's going to be H is equal to U cosinus alpha. U we
Okay.
have, alpha we have, cos alpha we calculate. Multiplied by U, we get our answer.
Thank you.
Okay, glad that's clear. But anyway, this was just a proof. You are not going to be asked to do these things. I was just doing that to help you guys understand why exactly the product mixed is going to give us the volume of the parallelepiped, the figure formed by the three vectors in that case.
And then on the value of U, is it that the determinant and the value of U, are they going to differ? Like where you have used H and on the other part?
Can you repeat your question?
Like where you have used the trigonometrical part, where you are saying that H, where you are saying that H is equals to U cos alpha, and then the U there, is it going to be the same value as the U in the original equation there?
Yes. It's the value in the original equation.
Oh.
Yeah, the module. You calculate the module of the U, because the U in the original equation, this one is a vector. It's a vector. These three are vectors. So this U is a vector. You just calculate its magnitude. The magnitude you get is what you're going to use there. That's why I was saying the U is given. The U is given in the expression here, in the question. It's already given.
So like, can you say that we are calculating like the volume?
Yeah, it's a volume we're trying to calculate.
All right, but how is it going to be wrong if you are to say that we multiply the V, the W, and the H just right there and then?
But where is the H coming from? You have, what we're trying to show now is where the H is coming from and what gives us the right to use the H as the height in this case. It's correct, you can just multiply it by the height, but someone might ask, why H? So what I was trying to show you guys is why H. You understand?
All right, I get it, yeah.
Okay, nice. Okay, we can get back to the lesson. You guys you can unpin the video. We are almost à la fin. So this was that, about this. Just have this expression then we go to the last part of the polycopy today, which is la derivation. I'm sure most of you that have done addition, not even now in the ordinary mathematics, there's also calculus 1, not so the whole thing for derivation and all that stuff. So this should be nothing new to you guys. It's just the same odd derivation that you know. You have one point, you have, or maybe, yeah, you have one vector going at one point, then the vector moves in time from one point to another, spending delta t as the time to move from that point to the other point. Now you have to calculate the rate of change of the position or the displacement from that initial point to that final point. It's the same odd differentiation that you know. So the first we're going to begin with is the ordinary differentiation with one variable. So they're telling you, excuse me, soit u de t égale OM, le vecteur u à l'instant t. Then now we're going to have u de t plus delta t. This one here now is the vector after the u has moved in time. It's moved from one position to the other. The reason why they've put plus delta t here is just to show you that it's taken this amount of time, delta t, to move from that one position to that new position. So it's moved from OM to OM prime. Okay, so maybe we have our O there, and we have our M there, and we have our M prime there. So the vector has moved from OM, where it was here, it's moved like that down there to OM prime. And it's taken exactly delta t to move from this point to that point. Why are we saying delta t? In math, whenever you see delta, just know you are talking about differences. So maybe at 1430, it was here. Then at 1435, it's here. So that there is going to be 1435 minus 1430, which is 5 minutes. So it's taken exactly 5 minutes to move from there to there, and that's the delta t, that 5 minutes. And when you're differentiating, what you're calculating now is the rate of change of position or distance. What was the rate of change? How fast was it changing? How slow was it changing? That's what differentiation simply is. You are calculating rates of change of this. If they say dy over dx, you're calculating the rate of change of y with respect to x. And the expression we normally use in calculus at the beginning is this one, d de u dt, which is going to be equal to limit. You are going to do limits in analyse. Limits lorsque delta t tend vers 0 over u t plus delta t moins u dt dt. As I told you, we are trying to calculate the rate of change of the distance in this case. So it moved from this position, u dt dt, ou bien OM, to u, or it moved from u dt, which is OM, and it went to u dt plus dt, or plus delta t, which is OM prime. It moved from there to there. So what we're going to get is a distance from there to there. We are going to subtract this distance minus that distance to get the difference in distance there, which is what is represented on top there. Then down here, we are going to put the time, because if we want the rate of change of the distance with respect to time, we are going to calculate the distance that was moved by the time that was moved. So we're going to know, okay, it was moving at this and this distance per second or per minute or per hour, depending on what unit you are using. The good news is no one really works with these things in mathematics. These are just there to help you understand exactly what differentiation is, what it's representing in life as you do your calculations. Because if you're just doing calculations, you don't know what you're doing, it becomes difficult. But if you know, as you are differentiating, I'm calculating the rate of change of the numerator with respect to the denominator. That way, questions become easier for you because you understand exactly what you're doing. So here they're just showing us, instead of using u t plus delta t and u de t, which is a bit more complicated. We are going to use the positions they were at. So the final position was OM prime. The initial position was OM. That means the distance moved was OM prime minus OM. And in vectors, when you subtract two vectors like that, it's like you're moving from this point to this point. It's going to be M prime, as in this case, because you are moving from OM to OM prime. So to that extremity there, it's going to be M prime, M prime. So the difference between OM prime and OM is going to give us M prime. I know it's written MM here, but I just made a mistake. It's supposed to be M and an apostrophe there to show that it's M prime. And M prime can also be denoted by delta OM to show you that it's a change in distance. Okay, as I told you, delta, it just represents change in something, the differences between two things. So they've written here delta OM to show that we are changing the distance from this point to that point. Finally, the expression is becoming simpler and simpler as we advance. D de I for dt, it's like the rate of change of u with respect to time is going to be the limit quand delta t tend vers 0 of delta OM, which was what we have here, OM prime minus OM, the change in distance, over dt, the change in time. And this expression, as delta t goes to 0, as delta t decreases and decreases and decreases and decreases, this triangle that we have here, this triangle, the delta, becomes a d. And now we can read it as d de OM sur dt. Okay? And they are telling us that d de OM s'appelle différentiel de OM. D de OM s'appelle la différentielle de OM. If you have never done calculus 1 differentiation before, there's a lot of Wi-Fi in Morocco. Just go to YouTube and just try to get or follow a lesson on calculus 1. This is very short. If you've never done it, it might confuse you. For those of you that have done it, I'm sure this is a piece of cake. But if you've never done it, I recommend that you just spare some time to do it. As I said yesterday, Mécanique du point, calculus and trigonometry are like a backbone. So if you are not well equipped in these two, this is going to be hell for you. Good news is that we have started early. You guys have a lot of time. Even you guys that have never done trig and calculus can still catch up to your friends that have done it by just simply putting in an extra effort on your own. Is it clear on this part here? It's nothing scary. It looks scary from a distance, but when you start doing it, you just realize it's obvious things. Numéro 7, differentiation. Okay, so differentiation in its essence is calculating the rate of change of something with respect to something else, with respect to one variable. So let's say I, Charles, run from my house to Carrefour. Okay, I have run from my house, I've displaced myself from my house to Carrefour. Obviously, I have changed distance there. I have traveled a certain distance, but I was from my home at 14 hours and I reached Carrefour at 14:10. I have moved from my house to Carrefour in 10 minutes. We suppose the distance between my house and Carrefour is like 5 kilometers. So I have changed my distance by 5 kilometers in 10 minutes. So now when you differentiate, you are finding the rate of change of distance with respect to time. If I moved 5 kilometers in 10 minutes, what was the rate of change of my distance? How many kilometers was I moving per second? because that's what's going to give you the rate of change of distance. You're saying, okay, so per second, Charles was moving maybe a kilometer. So you know that after every second, I was moving a kilometer. After every second, I was moving a kilometer. After every second, I was moving a kilometer. So you know the rate of change of my movement. It was 5 kilometers per second. And that's what differentiation gives us. Whenever they give you an expression to differentiate, that's what you are simply doing. When they tell you differentiate y with respect to x, you are calculating the rate of change of y with respect to x. How much of y is changing per x, per unit x, you can say. How much of x is changing per unit x? When x moves 1, how much is y moving? When x changes by 2, how much will y change? That's the rate of change. That's what differentiation simply is. That's why here we have this part here that's saying dde dt. We're trying to calculate the rate of change of the vector u with respect to time. How much of u was changing per second or per minute or per hour, depending on the unit you are changing. That's the rate of change. And that's what differentiation is. So we have our initial position at e dt. They have put the t here to show you that at time t, you were at u here, the first position, the initial position. Then we also have e de t plus delta t. That means after delta t now, you have spent a time of delta t. You are no longer at e, you are at e dt plus delta t. You have moved in time. If we are using this other representation, at first you were at OM, but you moved your vector from OM to OM prime. So you moved from this position to that position. And the distance that you moved is going to be the difference between this position and that position, which is OM prime minus OM, which is this one here, the expression here, OM prime minus OM. This one is just giving us the distance that we have moved, which is going to give us MM prime, or maybe delta OM, to show you that it is a change in distance from the initial position to the final position. And finally, we have our time. How much time did you take to move? At time t, you were at this position. At time t plus delta t, you were at this position. That means it took you exactly delta t seconds or minutes or hours, depending on the unit you have, to move from this one position to the next position there. What's just left now is for you to work out the rate of change, how much of the distance, or how much the distance was moving with respect to time, how much distance you are moving per second. If we get, for example, 2 seconds, how much distance were you likely to have moved? And that's what, that's the explanation basically of differentiation. The rest is just mathematical notation, expressions and all that stuff, significance or the application of differentiation. You are just calculating the rate of change of one variable with respect to another. So in this case, we are dealing with vectors. We are displacing one vector from one position to another, and we are displacing it in time. So they're just asking us how much distance we are moving with respect to time. And that's what differentiation is going to help us calculate: how much we have moved in time, how we were moving in time, the rate of change of distance with respect to time. So when we say here, dde sur dt égale dom sur dt, it's just going to give us the movement of OM with respect to time. Sav, I don't know if that's clear.
Kindly repeat.
Sorry. Is it clear?
Kindly repeat.
Yes, it's clear.
Okay, someone has said kindly repeat. Differentiation Differentiation, you are calculating rates of change of one variable with respect to another. So I gave an example of me displacing myself. Let's say I move from my house to the cafe, and I take 5 minutes to move from my house to the cafe, and the cafe is approximately my house. When you differentiate this expression I've explained here, you will be looking for the rate of change of distance with time, how I was moving in time, how much I was moving in time. So you say maybe per second I was moving 1 kilometer. That means that was, in other words, that was my speed. That's why we said that 5 per second, you are moving 5 meters, and that's what the speed is. That's what differentiation is about generally. You are calculating rates of change. You move from one point to another in time, and you're asking yourself, how much or how was I moving in time? How was I changing distance in time? You differentiate, you get your answer. It's not only restricted to distance and time. Sometimes we derive dy over dx. What we're calculating there is the rate of change of y with respect to x. How much was y moving per x? If I move x once, how much is y going to move? If I move x twice, how much is y going to move? That's the rate of change, and that's what differentiation gives us. That's the significance or the application, or what differentiation implies, or where it comes in handy. We are calculating rates of change. An application, for example, is in industry. I remember in additional mathematics, there was a certain question that was asking us to calculate. Uh, you have water going into a tank, and then you also have water leaking. Find the difference to see if the difference is significant. So it means you have to calculate the rate of change of the water leaking out and the rate of change of the water going in. So if the water going in is way, way more than the water going out, you find that, okay, it's negligible and we can leave that leak. But if you find that the water leaking out is so much that it's affecting the water going in, you know that, okay, this has to be fixed. So that's an application. You are going to use differentiation there to find the rate of change of the liquid going out with respect to time. How much of the liquid is going out per second? How much of the liquid is going in per second? That's the rate of change. And that's differentiation for you. As I said, you can try and get a mathematics book, go through calculus 1 and try to do some examples. So you're going to understand what we have here is just a short segment, because when you go to school, they are going to suppose that you have done calculus already. So they won't spend time explaining differentiation and all that. They'll just tell you, ça, vous le savez, vous l'avez déjà fait, et on le fait comme ça, and they advance. So if you have never done calculus, you'll be on the back foot, back pedal, while your friends are advancing. So it's better you look at it, you find some time to do differentiation and a bit of integration as well. Okay?
Oui.
So down here we have just some rules, some general rules in calculation or in differentiation. Number one is when you're differentiating a sum, when you have like d de u plus v, you can separate them. You can first differentiate you separate v, you differentiate v, then you add the two answers you get. It's the same thing as adding u and v first, then differentiating it. That's just how calculus is. Then secondly, it's multiplication by a scalar. You can either multiply the scalar. This lambda here is a scalar quantity. It's just like any number. You can have 5, you can have 2, you can have half, you can have whatsoever, 3/2. It's just any scalar quantity you can think of. And v is a vector. Okay. So you can think of this lambda as a constant. For those of you that have already done calculus before, a constant won't change anything, whether it's in the differentiation or whether it's out of it. And mostly we just prefer taking it out because it's just going to disturb our calculation. So if you have d de lambda v dt, it's the same as lambda outside. You just ignore the lambda, and then you have d. This is not supposed to be u, it's supposed to be v, d de v sur dt. These are the same thing. So if I have like, I'm deriving d over half t squared over dt, that half, I can take it out this side and I can just derive t squared. The answer is going to be the same thing. The next step is the product rule. The product rule states that if you are differentiating two products, you have u times v. What you do is you keep one constant, you derive the other, plus you keep the other constant, then you derive the other one that you didn't derive. As simple as that. So if you have d de u fois v dt, you have d de u dt fois v. We keep v constant and derive u. Then we say plus, then we are going to keep u constant on this v. That's the product rule. Then here we have, I don't know if we can call it the product vectorial rule, but this is just restricted to vectors because it's the product vectorial. It's almost the same as this one, except instead of having the scalar there or the multiplication, we have the product vectorial there, right? And keep the constant, but we calculate the product vectorial. Plus, this time around, we are going to keep u constant, and then we derive v and calculate their product vectorial, and this becomes your expression for this. So these are some of the rules of differentiation. Very simple to apply. When you do examples, you realize just how simple they are. Are these ones clear?
Yes.
Okay, so now we come to the last part. The last part here is a differentiation with respect to several variables. Because normally we differentiate and we have one variable, like a deriving dy over dt, dy over dx, and that's it. But in this case, we do not have one variable, we have several variables. So it's like a differentiating with respect to x, y, and z. How are you going to do it? It's very simple, it's very obvious. So when you have several variables, you're differentiating with respect to several variables, we use partial differentiation. We call it partial differentiation. So if you have an expression with more than one variable, maybe you have x, y, and z varying, what you do is, number one, you don't use d, like here we say d u over dt, v of t. No, we use this statistics. It does differentiation. So if I say, for example, f is equal to x, y, z, and all three are varying, how am I going to differentiate that? What you do normally is you first pick one variable. Let's say I begin with x. I will say d rond f, d rond x. That means I'm going to derive par rapport à x while I keep y and z constant. I'm going to treat those two like they are constant, like they're just any numbers, like they're constant to derive with respect to x. Then you say plus d rond f, d rond y. You are going to treat x and z like they are constants, and you derive par rapport à y. You are going to treat y like your only variable, keeping the other two constant. Then finally, plus, you go to your last variable z. You have d rond f, d rond z. You are going to treat x and y like they are constants, and you derive only with respect to z. And that's how you do your partial differentiation. Oh, there's no example here for a partial differentiation. Okay. I'm going to give you an example. We're going to do the same thing we did before. I'll try joining using my phone so that I get a picture of my calculations here. You can quickly try and look at it.
But Charles,
Huh?
may you just repeat on the last thing, the thing you just from explaining?
Okay. Instead of repeating, let me give you guys an example so that you try and understand better. I will do what we did before. You guys are going to pin my video. Just go to Charles Ngalandula and pin the video so that you are seeing it. You have done it?
Yes, we have.
Okay, so I have an example here. We are going to use partial differentiation to calculate it. Okay, so I have this question here. F is equal to 2xy plus 3xyz. So I have three variables here. I have three variables, x, y, and z. So we are going to use this expression here now to find the derivative. We'll use partial differentiation. Now what the rule of partial differentiation is, you are going to differentiate with respect to each variable one by one, keeping the others constant. So we are going to begin with this expression, x, the x is going to be equal to. So when you start doing this, we are going to treat y and z like they are constants. Okay, we're going to say y and z are constant. So we only have one variable in this case, which is the x. So come here, y constant, 2 constant, x is varying. So when you differentiate this, the x is going to disappear, not so. If y is being treated like a constant, the x is going to, when you differentiate x, is going to give you 1. So we'll have 2y plus. You come this side also, we are going to treat the y and the z like they're constants, just like the 3D side, just like a number, y, z, the way you treat numbers when you're differentiating. So we only have one variable, which is the x there. So when you differentiate this x, it's going to give you 1. So we'll be left with 3y and z. So it's going to be 3y, z. So you found your expression for d rond f, d rond x, dx. Then you come to the y now. The y dy is going to be equal to, you are going to treat, we're going to come here, 2xy. Since we are doing partial differentiation with respect to y, we are going to treat the other variables like they are constants and we only keep the y as varying. So the x is going to be a constant in this case. Our only variable is y. So when you differentiate the y, you're going to have a 1 there, and we're going to remain with 2x. So you write 2x plus. You come this side, as usual, we are going to keep y variable and the other variables, will treat them as constants. So x and z are going to be treated as constants. When you differentiate the y, it's going to give you 1. So you'll be left with 3xz. So you'll have 3xz. Then finally, we come to the last variable, we'll be differentiating partially with respect to z. The z is going to be equal to this. In this expression here, there's no z. So this entire expression will be treated as a constant, and we know the derivative of a constant is 0. So we'll have a 0 there, plus. Then we come this side, x and y will be treated like constants because our only variable is z. So when we differentiate z there, we'll have a 1. Then we'll run 3xy, so we'll have 3xy there. So your final expression for df, because df is equal to this plus that plus that. And we've calculated all of these three components, this, and that. So df is simply the sum of all those things. Df, the derivative partial, is going to be 2y plus 3yz plus 2x plus 3xz plus 3xy. Then we've differentiated with respect to three variables. That's how you do partial differentiation. It's very, very easy like that. Was that clear?
Yes, it was.
Yes.
Yeah. Someone said they were not clear. Are you clear now?
Oh, yes, I'm clear.
Okay, lovely. Nice and clear. Perfect. Perfect. So that's partial differentiation. The expression looks confusing, and though, trust me, I was also scared when I saw it. I was like, you're differentiating with respect to 2 or 3 variables. How are you going to do that? But when the professor actually explained how to do it, I realized it was simple stuff, very obvious stuff. And the expressions they're going to give you when you're doing partial differentiation, they're not even complicated. We have 7 minutes. By Monday, I should be sending you guys the answers by Monday or Tuesday, so you can just do it and keep the work with you, because if all of you send me your work, I'm going to have a lot of things to look at. Keep your work with you, then I'll send you the answers and you can compare. Where you have questions, you are free to ask. So you should try this exercise 2, try it out. Exercise 2, try it out, except for exercise question 4. Except for question 4, there's a mistake there. I didn't pose this question properly, so just skip it. Just 1, 2, 3, and 5. Then there's something I noticed gave you guys trouble. So I just wanted to I'll try and find some videos on differentiation. But if I don't see it, just go to YouTube. There's a lot of guys that explain.
Charles, just them.
That stuff. Because for me, I didn't do any. Someone was saying something.
Yeah, like, can you
Yeah.
also kindly give an example for the last rule, like on the differentiation?
An example for which rule?
The
For this
second
one?
last one.
The
Yeah.
one for Hodwi. Okay.
Yeah, the last one where they told you.
Okay, it's said differentiating vectors, so you might get confused. We can wait until we start differentiating vectors. When we start calculating velocity, acceleration, then I'll give you an example on it. So bon, because if I go there, I'll have to explain more things to you guys. So I'll give you an example when you get there. For now, you can just keep it as that.
C'est bon.
Okay, c'est bon.
Okay. Good. I wanted to go over something quickly. A tool we'll be using next week, and a tool you are using in electromagnetism, or electrostatic, I was following with you guys, and I noticed that these things, they confused you guys. It is these trigonometric projections. In mechanics, you just have to know how to do these things because you work with them all the time. You guys can see my screen, huh?
Yeah.
Yes.
Okay. So one thing you should know, or one thing you already know in trigonometry, it is that right angled triangles are like the gold mines of trigonometry. When you're working with right angled triangles in trigonometry, it's like you just landed on a gold mine because those ones are very easy to work with. They're the easiest figures or shapes to work with in trigonometry. Circles, squares, whatsoever else can be confusing. The math there can be complicated, but for right angled triangles, it's obvious. SOHCAHTOA, 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 Pythagoras theorem, all these things, been doing them since grade 8 and you know them. So right angled triangles are like the gold mines. And so when we are solving questions in mechanics, we always try our best. In fact, we do everything to work with right angled triangles. Whenever you are trying to resolve vectors, you're trying to resolve expressions, work in a right angle triangle. Any other triangle, you'll be doing complicated math. But you work in a right angle triangle, it's going to be very, very easy. So whatsoever repère you've been given, try, okay, I'm going to send it in the group. Whatsoever repère you've been given, try by all means to figure out where a right angled triangle is there. Whatsoever you're trying to work out, if let's say, for example, you're trying to work out a rho, this vector here, or rho, you're working with it. Try to create a right angled triangle with rho there, okay? Try, just search for it, look for it, you're going to find it because mostly the repairs you're working with, they are orthogonal. So they're meeting at 90 degrees. So there's 90-degree angles all over. You just have to look for them. So when you find one, your calculations become easy. So that's a petit rappel here. We have this right angle triangle, we have the right angle there, and we have another angle here, theta, and we have the adjacent side to theta, we have the hypotenuse side, and we have the opposite side to theta. Sure, this is nothing new. Then we also have SOHCAHTOA. So we know the sinus of theta is the opposite over the hypotenuse. So the cosinus of theta is going to be adjacent over hypotenuse. Then we also have the tangent of theta is going to be the opposite over, sorry, I made a mistake, it's supposed to be adjacent, not hypotenuse. Opposite over the adjacent. That's TOA. Okay, so you are going to work with these things. The moment you locate your right angled triangle when you're trying to resolve vectors on a plane or in a repère, when you locate your right angled triangle, all you'll be working with is this SOHCAHTOA, SOHCAHTOA. And this is relatively easy to work out. So that's why when you are doing electrostatic with Chawanzi, you are projecting Y, you move it here, you project X, you move it there. It was because right angled triangles are easy to work with. So we try to locate our work. So the first example you are going to meet in mechanics and electrostatic was this one. It was this one you met. You have X, Y, and Z, and another vector between Y and Z, rho. Okay, and you're supposed to work out rho, n'est-ce pas? You're supposed to find the expression for rho. There it is. Now, where are you going to start from finding the expression? So the first step you're supposed to do is try to put rho in a right angled triangle. Okay, you're supposed to try and put it in a right angled triangle. Or there's one thing we know, it is that these axes, they'll tell you orthogonal. They will tell you in the question, it is orthogonal. So we know they are all at right angles with each other. Between X and Z, there's a right angle. Between Z and Y, there's a right angle. And between X and Y also, there's a right angle there. There's a right angle there. Okay. And one thing also you should know about vectors is parallel vectors are equal. If you have two vectors that are parallel, they are the same thing. So if I get this Y and I move it up here, as long as I haven't changed its direction, it is equal to the Y out. They have the same direction. They are the same. So if I translate this Y, I move it there without changing its direction, it's still Y. It's still valid. parallel vectors are equal. So here, I'm trying to put a hole in a right angle triangle. I need to find a right angle is going to are orthogonal to each other. They are meeting at 90 degrees. So if I get this y and I move it down here, okay, I translate it down here. I just draw dotted lines there. I move this y, I move it down there, and I connect it x and whole. The y was meeting the x at 90 degrees. So if I translate it there, I project it to this, it's still, so you see, I have formed a right angled triangle there, x, y, and whole with a right angle there. And I can extract it there, x meeting my y at 90 degrees, then I have my whole as the hypotenuse. And I had this angle that was given between whole and x, which is phi. So from there now, you can just use SOHCAHTOA to work out. You know that phi is going to be equal to sinus phi of something, or is going to be equal to this and that. From there, it becomes easy. Not so. It's clear on this one.
Yes, it's clear.
Yes, it's clear.
Yeah, that's that. And also learn to extract your work from the figure. Some people will try and work from this same place here. You'll get confused, okay? Because when you look at this, x and y there, they're not looking perpendicular, and you might get confused. So try to extract it, move it to a separate space, draw the figure properly, and then continue your working like I've done here. It's going to help you. Then sometimes you meet figures appearing like this one. So you have your x and y still orthogonal, meeting at 90 degrees. Then you have this vector down this side with a totem vector that's down here. As usual, you are supposed to look for a right angle triangle because your calculations will become easier from there, okay? A right angled triangle. So what we know about y is there meeting x at 90 degrees. I can translate this y this side. It won't change anything if I move it to this other extremity of y because it's still going to be parallel to this. So that's where I moved it there, using dotted lines to show that it's just a projection of this y there. And then vectors that are parallel to each other but in opposite directions, they are equal but have different signs. So if I have one going to the right and I have another vector going to the left and they're parallel to each other, the one going to the right is equal in size, but it has a different sign. So one might be 5, the other one will be -5. One will be 4, the other one will be -4. One will be I, the other one will be -I, but they are still of the same size. So after I translate this y this side, the value is going to be the same. But I want to form a right angle triangle with this line here, so I can translate this y to make it go in the opposite direction. And when I make it go in the opposite direction, I will change its sign. It's going to become negative now. That's why here I wrote -y now, and voila, I have formed my right angle triangle, and I can simply work out this vector now after I have formed that right angled triangle. Then lastly, we have this. Sometimes they appear like this. You have a vector there, you have your y, and you have your x there. And perhaps they want you to work out this vector next to the y there. Again, your aim should be to put it in a right angle triangle so that you easily calculate it using SOHCAHTOA and whatsoever operations come with right angle triangles. So what you're going to do now, in this case, we'll be translating the x or projecting the x. So because this vector we're looking at is in the opposite direction of the x, we are going to make the x face the other direction or go in its opposite direction like that. And it's going to become -x, okay? And then afterwards, we have seen that, oh, the right angle triangle has not been formed. If you want, you can translate it here to be right, or it's two parallel lines and they are equal vectors. So what I did for me was I moved the x up there, and that's why I have this final figure here in a right angle triangle, and I have my angle theta there, as in the angle theta there. I just didn't include it here, the angle theta, and I have this vector I'm looking for. And I can use SOHCAHTOA, Pythagoras theorem, I don't know whatsoever operations you want to use to calculate this vector, but they are going to be easy if you put them in a right-angled triangle. So whenever you're working with these repairs and you're working out vectors, you're finding expressions for these things. Put them in a right-angled triangle. Look for a right-angled triangle. Translate, project, do whatsoever you have to do. Form a right-angled triangle. As long as you're following the rules, don't change figures. As long as you're following the rules, they have to be parallel. If they're opposite, you have to indicate it using a sign. And that's that. This is that about this. If there are no further questions, we have come to the end of our lesson. Are there questions?
No.
Okay, lovely. I don't know if it's true there are no questions or people are just tired, but we will find out soon. But thank you for your attention. I hope it was clear. And we have come to the end of our rappel mathematique. Tomorrow we'll be starting the Mécanique du point now, the first chapter, cinematic. So if there's nothing else left to say, I wish you all a good day and on se verra la semaine prochaine, mercredi, Inch'Allah. How did you become that good? Good at Betrayal.